All right. So in the start of this chapter, we did addition and subtraction, and then we did multiplication. Now we will work our way towards the division, which is sometimes referred to as the multiplicative inverse. How do I invert multiplication? Because flat out division, just imagine, remember how you multiplied, row by column? That'd be really hard to undo that. Okay? And so we're going to do what's called the multiplicative inverse, and we're just going to learn about it today, and then we'll actually apply it as the time goes on. Each square matrix will have something called a determinant. What it determines is whether or not that matrix has an inverse, because not all of them do. Okay? And so to find a determinant is actually quite simple and does sometimes have different notations. So here this DET does mean determinant of this 2 by 2 matrix. Okay? And so another way they could write it is it almost looks like they put it in absolute values. That's the same thing if you see something like that. It means find the determinant of that matrix. And seeing it as a square matrix, we can at least try. Okay? And that, in fact, they will all have a determinant. It's just whether or not they'll have an inverse or not is in question. To find the determinant of a 2 by 2 is actually quite simple. What you do is I kind of call this the positive diagonal. You take the 7 times the 6. So I kind of consider that the positive diagonal, and then that happens to be, well, maybe I'll write it out for you. And then this I would consider the negative diagonal going the other way, which is 9 times 3. But you have to subtract whatever you get in that particular diagonal. Okay. So in this case, the determinant is the number we end up with in the solution. So in this case, we've got, what, 42 minus 27. So what is the number that we actually end up with? 15? So this has a determinant of 15. So I can tell you right now, I have determined that that matrix does have an inverse. There's only one number you don't want to get as the determinant, and that is 0. If you get 0 as the determinant, that matrix you just got does not have an inverse. And you will see why in just a little bit, why a determinant of 0 is a problem. So this one will have an inverse. Again, all I had to find was the determinant here, and so it is 15. Okay? And it has basically determined that it does have an inverse. Okay. 2 by 2 is quite simple, and that's why sometimes they forget it when they get a 2 by 2, because they're so used to getting a 3 by 3. Okay. When you get a 3 by 3, it does get a little bit more complicated. You basically just have more diagonals. You're going to have 3 positive and 3 negative. Okay. The very first positive is quite simple to see. It's just this one here, and you go ahead and you multiply all of them. So that's your first positive. So you take negative 2 times negative 3 times 4. Okay. Is it okay if I don't write that out and you just kind of know that's what we're doing? Are we good with that? Okay. So I like to do it this way. It's a negative times a negative times a positive. Well, what's the end result there? Positive or negative? It's going to be positive, right? So now we know it's positive. So let's just go ahead and take 2 times 3 times 4. Well, 2 times 3 is 6 times 4 is 24. So that would be one of our positive diagonals. Oop, I shouldn't have written it there. So hopefully you didn't either. Write it underneath. So that's my fault. Because now what we're going to do is we're going to go over to this 4, and we're going to try and make this next diagonal, but you notice how there's something missing right there? There's nothing down there, right? I look at it as you can kind of wrap yourself around the matrix, and it actually comes back to this number. And that gets kind of confusing if I kind of wrap around and it comes back to there. So what we tell you to do is take this very first column right there, where it goes negative 2, 4, negative 1, and just rewrite it over here. Because now do you see how it comes down and it hits that negative 1? Okay. So sorry if your 24 is in the way. That's my fault. So that is our second positive diagonal. So you take a positive times a negative. The end result is negative. So you can put plus a negative or just subtract, whatever you're comfortable with. And then you have to fit 4 times 2 times 1. Well, 4 times 2 is 8, times another one is 8. So once again, we go to find our final positive, and we go this way, but then once again, we're missing this location here. And so what we do is we take the second column and rewrite that one. I took 4 times 2. I took 4 times 2, I think you added if you had 6. Yep, 4 times 2 times negative 1. Yep. The question there was how I got negative 8. So now we take a negative times a positive in this column, because it's negative 1 times 4 times 5, and that's going to be negative result, and then take 1 times 4 times 5 is 20. So do you notice that the positive diagonals don't necessarily end up being positive? It's just what I refer to them as the positive diagonals. Do you believe it matters which order you find those in? Or can you find them in any order you want? Yeah, you can find them in any order you want, just make sure you have the correct sign on them. Okay? I like to have some kind of organization with it. So now we'll try and color code things. We'll go blue. Now that you have all these extra columns in there, it's actually quite helpful to get the negatives. So you start wherever you want. I normally start on this side to get my negatives, and you just go this way. So you take 4 times 4. Well, it's a positive times a positive times a positive, which is going to be positive, but watch out. So we're going to take 4 times 4 is 16. Does anybody know what 16 times 4 is? 64. We have to subtract whatever I get because it is a negative diagonal. You subtract whatever you get, and I got a positive 64. Okay. Next one is another negative diagonal. So you take negative 2. Well, it's a negative times a positive, which is going to be negative. So I'm going to subtract a negative here. Because the subtraction comes from right here. It's a negative diagonal. Okay. And then you take 2 times 2 is 4 times 5 is 20. And we have to just finish off with our last one, which is right here. So it's a negative times a negative times a negative, which in itself is negative, but then I have to subtract it because of that right there. So I'm subtracting a negative, and what do we get? 1 times 3 times 1 is 3. Sorry about this, subtract a negative over here. It looks like an equal sign. That's better. Okay. So now what we have to do is figure out what number we're looking at. And sometimes people like to clean it up because of all the signs. So really we have 24 minus 8 minus 20 minus 64 plus 20 plus 3, right? Because it's add the opposite. Right? And if I was doing it, I would kind of look at it as this negative 20 and positive 20 just cancel. Okay, so you don't have to worry about those. So this answer appears as though it's going to go negative. Is that okay? Can a determinant be negative? Sure. Okay. Determinant can be any number. Okay. And what number did you get when you completed your calculation? Negative 45, I heard? Okay, and what does that determine? That there is an inverse to this matrix. Okay. It helps you more in just determining, but that's the first thing it does. It determines that there is an inverse. Any questions so far? Okay, why don't you go ahead and practice on the next example. I will pause the recording, and actually if you are listening to this, actually please pause it instead of just getting the answer. All right, here we go. Let's see how you did. Hopefully you actually did do the problem instead of just waiting for the answer. So again, it's probably best when you have one of these is to just copy down the first 2 columns and go. So this is what, a positive diagonal or a negative one? Positive. What'd you get when you took 8 times 5 times 4? 160. Very good. Here's another what? Positive. And so it's a positive, but it's really when you end up multiplying becomes negative what? 63. And then we got our final one, which is actually going to be positive, and it is what, 18? Any questions on the positive diagonals? Okay, again, it doesn't matter which order you go get these, but let's go ahead and just go that way. So I'm going to subtract whatever I get on this answer. And so I'm going to subtract what? 108. Then subtract whatever you get doing the next one, which is 112. And subtract whatever you get in the last one, which is a negative 15, right? And so really, plus 15. Okay. What did you find out? Does this particular matrix have an inverse? Yes, it does, because the determinant is negative 90. Okay. So it does have an inverse. Now, for the purposes of this class, the only ones I'm actually going to ask you to find the inverse by hand is if it's a 2 by 2. You can do a 3 by 3 by hand. It's just a little bit more than what we need to do in here. Okay? If we ever need to do a 3 by 3 by hand, we'll use technology to do that for us. So notice here it says inverses of matrices. If the determinant does not equal 0, that's what that symbol is, does not equal, then it has an inverse. Do all the above matrices have an inverse? Yes, they do. What kind of matrices can have an inverse? Well, to have a determinant, it has to be square, so it'd be square ones. So if this was your original matrix over here, you better get good at reading this stuff, because as you move on in school, you never know what kind of teacher you're going to have. So it says if matrix A looks like that, A, B, C, D, and the determinant of A does not equal 0, then the inverse is 1 over the determinant of A, and then you have to be able to read what happened here. What happened there? It started off A, B, C, D. Now it's D, negative B, negative C, A. So we can kind of paraphrase what happened there. Yes? Very good. Switch A and D. Notice they were here, and now they're in opposite locations. And then B and C stayed where they were, but they changed their signs. Okay? And then this matrix, when all is said and done over here, will be the inverse of the original. Okay? Which is basically how we're going to have to divide. This is really the only way to make that work out. So let's try one. Find the inverse. So as it says, step 1, let's calculate the determinant, because why would we try this if the determinant was 0? So here we go. It is 6 minus, because this is a negative diagonal this way. Not sure why I made it so thick. Minus, what, a negative 4? So the determinant is 10. So does it have an inverse? Yes, it does. So now we have to use that formula that said, if the determinant's not 0, to find the inverse, so we'll maybe call this matrix A. So A to the negative 1, or the inverse, is 1 over that determinant. And that's probably the most forgotten, is that 1 over the determinant. Now, as we were told, spots A and B have to switch locations. So here's kind of A and, oh, actually A and D, excuse me. A and D switch locations, so the 2 goes up here in row 1, column 1, and the 3 goes down there, row 2, column 2. And B and C simply, they stay where they're at, but they change signs, and so it's positive 1 and negative 4. There is no need right now for you to multiply these out, because could I do the scalar multiplication of 1/10 times all of those? I think we can all handle that. But let's leave it, because what we're going to use this for, we're not going to want to do that. Okay? So any questions? That is the inverse. Yep. 1 over 10 times the matrix 2, 1, negative 4, 3 is the inverse of. So like A to the negative first equals like A to the right, that's a notation. Yep, A to the negative first out here, this is just a notation that means it's the inverse of A. Okay. Now, so this is A to the negative 1. Here's an interesting question. This is A to the negative 1. What if I were to take that times A? Just out of curiosity. When you take something times its multiplicative inverse, what do you end up with? Just in general. Yeah, you end up with 1, right? For example, if I just had a regular real number of 3, what's its multiplicative inverse? 1/3. So when you multiply, you get 1. But what does 1 look like in matrix form? What does 1 look like? Well, somebody just said 0, 0, 0, 0. But then if I ever multiply something by 0, 0, 0, 0, I would get 0. Ooh, 1, 1, 1, 1, we're getting closer. Well, somebody just splat out a bunch of stuff, and I'm not really sure what it is. What you would end up with is what's called the identity matrix. Okay? The identity matrix is that. It will be that first positive diagonal will be all 1s. Okay? The reason that works is if I take anything times that, so let's say I had a matrix 1, 2, 3, 4, and I took it times this. Do you agree? If I take row by column, I'm going to end up right back with 1, 2, 3, 4 as my final matrix if I take it times the identity matrix. I'm going to end up with the same thing because of all the zeros that are in it. So is it possible to have, say, a 5 by 5 identity matrix? Yeah, why wouldn't you be able to? Okay, that means you'd have 5 equations, but a 5 by 5 identity matrix.
So 1, 0, 0, 1 is the.
It's a form of 1. This is the same thing as anything else, that 1 can come in many forms. That is also 1 in matrix form. It's just a bigger version of it.
But that's what you get when you multiply.
Yes. Yep. In this case, when I take these two times each other down here, let's think about this. This is a 2 by 2 times a 2 by 2. So can I actually multiply? Yes. How big's the answer? 2 by 2. There it is. Okay. So, try that one on your own right now. Again, actually try it. Don't just wait for me to put the answer on the board. And pause the recording if you're actually listening to it. It looks as though most of you had enough chance to work on that. So to find the determinant, we got what? -2 minus whatever I get going this way, which is 12. Agreed? So my determinant is -14. So to find the inverse, because now we know it has one, to find the inverse. So again, if this is b, this would be b to the -1. It means inverse in this case. It's a notation. It would be 1 over -14 times the matrix. 2, -4, -3, -1. So that is the inverse of the original matrix. Questions? So why is it that the determinant is not allowed to be 0? Nope. The answer there was the whole thing would be 0, and that is incorrect.
Dollars on the table. No negative zero.
Nope, it's not because there's no -0.
There's $10 on the table.
Okay, not somebody said something, but not everybody here knows what that means. But it's 1 over the determinant. If the determinant is 0, it's 1 divided by 0, which is the one thing undefined in mathematics. Any other questions?